Okay, so instead of having a real D20, because for some reason I could not find one, I have a fake D20 here on the screen. Okay, so what I'm going to do is we're going to rotate. I'm going to get a pen so we can track this marker. We're going to do a couple of rotations to this die, all right? And then we're going to do them and we're going to reset the die and do them in reverse order. And we're going to see if we get the same result. All right, so our starting, we'll say our initial position is just a D20 normally, so I'm just going to write it like this. We have a triangle, we'll have a 20 in the front, and we've got a 2 here on the side. And what do we got? An 8 and a 14 upside down. An 8 and a 14. Can I write 14 upside down? Good enough. Okay, so we need to define how we're going to rotate this system. Okay, so we need to define an axis system. So let's just use the one we always use. X, Z, and Y. Okay, so Y is out a little more. And what I'm going to do is do some sequence of rotations along each axis one at a time. So we'll rotate, for instance, the die along maybe 90 degrees along the Z-axis, and then we'll rotate it around the X-axis, see what the end result is, and then do the X and the Z rotations inverse, in the opposite order. Okay, so let's do that first. So step 1, let's just do a 180 degree or pi rotation around Z. What does that mean? Well, that means we're going to rotate it like this. Okay. And I'm just making these up. I'm hoping this works out, which I think it does. And then what we'll do is we'll do a 90 degree rotation around X. Okay, so then we'll do one more along this. Then we should be careful if we're going to go clockwise or counterclockwise. So let me be consistent about that. Let's be clockwise. Let's just do clockwise in every direction. Okay, so let me say that, clockwise. Clockwise. Of course, a clockwise 180 rotation is the same as a counterclockwise. It doesn't matter, but let's just be consistent. Okay, so let's go ahead and do each step. So what's the result of the first step? We're going to rotate this die 180 degrees on its axis. And let's see if my pen will allow me to do that. No, okay, I have to use my mouse. Oh, that's the wrong axis. Sorry. It's much easier to do this. All right, that's good enough. All right, do you guys agree that's 180 degree rotation around this axis of the ring? We just flip the die around. Okay, so let's go ahead and draw that. I like my pen over here. All right, so now we have a vertex in the center instead of a face. How many edges do we have? 5. Right, so we have a vertical like this, and we have this and this, and then we have 7, 17, 10. What's that one there? 12. Can I write a 2 upside down? That kind of looks like a 12. And then what's that number right there? Is that 16? 15. 15. Okay, so that's what it looks like after we rotated 180 degrees. And now what we're going to do is we're going to take the die in this orientation and rotate it 90 degrees clockwise. So we're going to rotate this way. Okay. So now we're going to do step 2. Okay, so we're going to rotate this way 90 degrees. So that means that this little vertex in the center is going to be pointing up. Okay, and there's our result. All right, so our end result of this is says an upside down 7, no, correct 7. And we're left with an upside down 1. All right, we'll just leave it like that. That's not really a 1. Just upside down 1. Is it left or right? Oh, sorry, I have the orientation of that little jagged edge. Sorry, there's the one. And then what do we have on the other side? We have a 17 over here. And what's on the left of the 7? 15, thank you. I could probably figure it out from this, but I'm lazy. 13, and what's all on the right then?
19.
19. Okay, thank you. Okay, so what we're going to do now is we're going to do the same thing, but we're going to flip step 1 and step 2. So let's reset our die. I'd say that's close enough. Okay, so we're here, and now what we're going to do is do step 1 prime, which is a clockwise 90-degree rotation on X. And step 2 prime is a clockwise 180-degree rotation around Z. Okay, so let's do step 1. So again, we're going to rotate it this way. So that 20 should be pointing directly up. There we go. So again, we get a vertex. And what do we have? We have a 9, upside down. What do we have? We have a 14 up here, upside down 14. It's really hard to write numbers upside down. We have an upside down 4 here. And that's a, what is that, a 6 there? What is that number? Oh, it's a 9. Oh, wait a second. What's the difference between these? That's a 9, that's a 6. Okay, sorry. So 6. And then what is that, 11? Okay. All right, so now let's do the last step, step 2 prime. Sorry, this is step 1 prime. 2 prime, so now we're going to rotate counterclockwise 180 degrees around Z. So we're just going to rotate it 180 degrees around this axis. So this vertex is now going to be pointing backwards. Right? And this is where we end up. We end up at another vertex. Where we have a 3. Basically, what is that, 17? 10, 8, and 16, right? Right, well, anyway, I don't really have to write this. This is step, what is it, 16? 16, sorry, thank you. I don't have to write them precisely. You can already tell, right? This is our end result going step 1, step 2. And here's the other result going backwards. Different ends, right? They're different. And then, of course, the question is what do we need to go from here to here to connect them? But there's at least one more rotation in order to come back to the original point. Right? So this is proof already, right? I've just proved it. Rotations in 3-dimensional space are not commutative. I just have to do it. I just have to do 2 steps, and already I end up at a different spot than I did when I do it the opposite direction. This is why angular momentum doesn't commute. Precisely the same reason. Rotations in 3 dimensions aren't commutative. So if you think about the algebra of rotations, how do you rotate things and how do you do math of rotations and stuff, that algebra, unlike normal algebra, is not commutative. It's a non-commutative algebra, and it has an entirely different set of rules about how products and division and all the different types of algebraic manipulations you can do are different because you don't have the law of you don't have the commutative property anymore. So rotations are not commutative, and therefore this principle right here is entirely the reason why we can only know one direction at a time. The only commutative combination of angular minimum operators that we can pick is one direction and the magnitude. I don't really care about the magnitude here because it's not a rotational quantity, it's just a magnitude. So in terms of direction, you can only have one. Because again, because they're not commutative, the moment you include two dimensions, 2 rotational axes, everything starts to get mixed up. You get the non-commutivity of rotations. So that's why we can only know one direction of rotation of angular minimum, is exclusively because of this. Interestingly, I won't prove this here, but if we look at objects in 2 dimensions, so like a board, I don't know, think of anything, a clock face or something like that. Rotations in 2 dimensions are commutative, right? Because if I go, so for instance, if I start here, and then step 1 puts me here, and step 2 puts me here, and so let's say this is 45 degrees, and this is another 45 degrees. Well, it's not hard to see that if I flip 1 and 2, I get the same result. Or if I do 60, let's just do them slightly differently. Right? The net rotation for this, the net, is a 105-degree rotation. And that's equal to 60 plus 45, or 45 plus 60. It doesn't matter, right? It doesn't matter which way you rotate in an xy plane. They're always commutative. Because you're just adding angles. You can't do that in 3 dimensions. Right? So if you had angular momentum in 2 dimensions, you can actually, well, if you have angular momentum in 2 dimensions, you only need to know one direction. And a magnitude. But in 3 dimensions, it's no go. Right? No go. Just by definition, it's no go. Okay, so this is why we're limited in the information we have about rotation and angular momentum, because that's what 3-dimensional space gives us. Any questions about this? I love this. I love this example. I didn't really understand non-commutivity until someone showed me this example, and it changed my life. Makes a lot of sense to me. All right, how you connect angular minimum to rotations is a little more elegant and a little more precise. That we're not going to worry about it too much, but you can imagine that you can think about the act of rotating something very similar to giving something angular momentum. It's not too hard to think that way. It's not a big stretch. Okay. So, what else can we do with this information? So again, the thing that we learned is that the orbital structure of our electron in our hydrogen atom, right, the s, the p's, and the d's, and so on and so forth, those, of course, come from the angular minimum. Right, we showed that 1 unit of angular minimum gives you the p orbitals, 2 units angular minimum give you the d orbitals, and so on and so forth. Okay, so what else can we learn about? What else can we learn about our hydrogen atom? If I can find my notes. What else can we learn about our hydrogen atom using this idea of angular minimum? What other ways does the hydrogen atom spin? What other kind of spinning operations does it have? And so this will allow us to bring, if I can find my damn notes for this, I have this beautiful handout that I printed out, and now I can't find it anymore. I apologize. Really big. Here we go. Yes, excellent. Very good. Exactly what I want. Okay, so I want to talk about one more aspect of angular minimum about an electron. All right? So again, an electron, if it were by itself in a box, there's no proton, it's not bound to anything. There's no way to spin the system. Right? There's no way to, remember, an electron is just a little point. It has no shape or size. There's no real intrinsic way to spin or to cause an electron to orbit unless you have it tethered to something, right? Unless you have that tether. Otherwise, it's just kind of moving x, y, z, and it's just going to do its thing. But it turns out that if you take free electrons and you try to get them to spin on their own, you invoke some angular torque to them, and they result in having different angular momentum states, despite the fact they're not attached to anything. And what we find, let me show you a really interesting experiment. And you'll notice that this experiment is very similar to our color and flavor experiment. But there's something that people realized about electrons, that they have some sort of intrinsic angular momentum to them regardless of the fact if they're bound to an atom or not, completely free. All right, and so the experiment I want to show you today, very, very simple experiment. And it's, again, exactly, excuse me, it's exactly the same as our color flavor measurement. But this is what's called the Stern, named after its inventors, Gerlach experiment. And this is a really, really wonderful experiment that really illustrates the intrinsic angular momentum of electrons. The idea is that angular momentum, electrons have they spin. They have some spinning momentum to them at all times, regardless of what you do to them. No matter what condition they're in, they show this behavior that is consistent with having some fixed amount of angular momentum. And let me show you how this experiment shows it. All right, this was done in the 1910s, 1920s, and it wasn't done with electrons, but it was done with silver atoms, which show the same property. But the idea is very simple. Is that we take an electron gun, which I draw as an actual gun. Of course, an electron gun is not an actual gun. If you've ever owned a CRT television, an old tube television, the thing on the back of the phosphor, the thing that shoots the electrons, is an electron gun. So literally you can just pull one out of a TV and it shoots electrons at you. And the idea is that this gun's going to shoot out a bunch of electrons, right? And it's going to do it in such a way that they kind of scatter. Okay, and then what I'm going to do is I'm going to filter them out a little bit by including a small wall here with a slit. And the slit's not important, but the important thing is that it collimates the electrons, so the only electrons that move through the system are all moving in the same direction, right? We make a beam of electrons. Okay, and what we're going to do, I need to define, what we're going to do is we're going to pass the electrons through a magnetic field. And we're going to pass it through a completely garbage magnetic field. I'll explain what I mean by that. What we want is a magnetic field that is very inhomogeneous, which means that it has a different magnetism at different positions. All right, so here is what my little magnetic tube looks like. It's got a positive electrode and a negative electrode. So this is my negative electrode. All right, and the electrons, let me color the filter electron so it doesn't confuse you guys. I don't want to keep the colors consistent. I'm going to change my filtered electrons to orange here. Right, the electrons are passed into this magnetic field. All right, and I'm going to define the magnetic field to be on the z-axis. So this is z and this is minus z. Okay, and I'm going to choose a magnetic field that is very inhomogeneous. What that means is that that basically all the electrons, as a function of how they enter, they feel a different magnetic field. So they basically get randomly thrown around. Okay, so they're not all, it's not like an NMR where everything is perfect. All right, so these are really crappy magnets that cause scattering of the atoms because there are some regions of the magnet are more positively charged than other ones. It's inhomogeneous. It's just kind of messy. And so the idea is that it's basically going to spread the electrons back out again using the magnetic field. So we can kind of represent the trajectories like this. Like some electrons might go this way, some might go that way when they come out. Okay, and then on the other end, I'm going to add a detector right at the end of the thing, which is just a wall. Right, this is my detector. Right, and it's going to light up. It's like a phosphor, like the screen on your CRT television. It's going to light up when an electron hits it. And what you see in this experiment, okay, so let me stop for a second. If these were classical objects, right, the electrons are classical. Remember, electrons are magnetic because they have a charge, and if you put a charge into a magnetic field, of course, it's affected by the magnetic field. That's the whole point. So if you were to have a classical if the electrons are classical, there's normal particles, on average, the deflection is going to be 0. Some are going to get deflected up, some are going to get deflected down, but on average, you would expect to see everything kind of on the mean of the deviation would be right down the center. Right? So classically, we would predict a result. This is a classical prediction that we would expect that the distribution of our electrons looks something like that, right? It has some width, but on average, the mean, right? Because they're randomly kicked up or kicked down. On average, they're just going to kind of go through the middle, right? That makes sense, right? But what do you see actually? What does Stern and Gerlach observe? What do they actually see? I'll just draw the detector again. So the actual result, the quantum mechanical result, is you don't get a mean in the middle, you get a bimodal distribution. So what happens is that either, and I'm going to just draw a line to show you that what they find is that no electron shows up in the middle. They only show up at the two edges. And the distance between the center of the detector and the humps are equivalent on each side. So they either get deflected by some amount up or they get deflected by some amount down. They don't go through the middle. There are none in the middle. So they either all are here, right? So in fact, you can do a count, and what you find is that 50% of them here and 50% of them are down here. Right? None in the middle. Just write that just to be explicit. 0% in the middle. Very strange. But the solution to this is actually very interesting. The idea is that this magnetic field is providing some sort of angular torque to the electron's trajectory, right? It's deviating by some angle from straight through. And the idea is that the electrons deviate by some angle or some torque either in a positive direction or equal and opposite in the opposite direction. There's only two possibilities, up or down. So there's a positive angular momentum contribution. You can think of the ones going up are sped up in an angular fashion, and the ones going down are sped down, slowed down in an angular fashion. So there's a plus and a minus contribution. All right, and let's try something different instead. So these are, again, electrons. And then what happens instead if I replace them with nitrogen atoms? This is really cool. This is one of those things they don't often tell you about. But what if I instead replace E with nitrogen? Just a nitrogen atom. Okay, so here are my nitrogen atoms. I'm just going to draw the detector. So the detector result is we see a slightly different distribution. We see some particles there. We see some in the middle. And then we see some at the edge, like this. And we see 33% here, 33% here, and 33% here. So some particles deviate with a plus combination, some deviate with a minus combination, and 30% of them deviate with no deviation. Right? So this is nitrogen atoms. Okay, so nitrogen has something obviously different. Nitrogen interacts with the field, the electric field, the magnetic field, sorry, slightly differently than the electron does. The electron gets 2 peaks at the edges, but the nitrogen gives me 3 peaks, including one in the middle. Very interesting. So we have a particle that gives me 2. Basically, what this means is that the electron has 2 states. We're going to interpret these as angular momentum states, some sort of spin. Right? It's applying some torque in some direction in an angular fashion. That the electron has 2 of these angular momentum states, and the nitrogen atom has 3 of them. And you can try different atoms and different particles, and you'll see that they show similar patterns depending on the atom. For instance, interestingly, this is a really cool one. I like this one in particular. If you do this with carbon-12 instead, so you replace nitrogen with carbon-12, and I should be explicit where this is nitrogen-14, which is normal nitrogen. If you do this with carbon-12 instead, which is regular old damn carbon, what do you see? You see nothing on the edges and 100% in the middle for carbon-12. Right? It looks like there's only one angular minimum state. And that angular minimum state is 0 angular minimum because it's not being deviated at all, right? It's just going straight through. Okay, so carbon-12 itself doesn't have this intrinsic angular minimum, but nitrogen-14 has 3 of these angular minimum states, and the electron has 2. All right, and you can try different atoms and you get different results. All right, so what is the interpretation of this? Well, the interpretation of this is that these objects have some sort of intrinsic angular momentum. So atoms, and in fact all particles, electrons, all atomic or subatomic particles, doesn't matter which one you choose, they all have this for the most part. There's a few exceptions, but they're very, very few. All atoms, atomic or subatomic particles, have an intrinsic angular momentum. They are always spinning. Always spinning, regardless of the conditions that they're in. Completely free. No matter what you do with an electron, it always has these 2 angular momentum states. And what do we call these? Right? This is what's called spin. Angular momentum. Spin. Every particle has a spin. The protons, well, the electrons has 2 spin states. Right? There's 2 spin states in the proton. Or in the electron, there's also 2 spin states in the electron, or the proton, sorry. And the nitrogen has 3, and carbon-12 has 1. Right? And so people saw this. They saw these patterns, and they're completely reproducible. It doesn't matter what temperature you're at, how fast you accelerate them, how big your magnetic field is, how good or poor it is. It doesn't matter. You see the same deviations for every electron in every place in the world at all times. Nothing changes. It's completely fixed. Not only that, it doesn't seem like, remember with our electron bound around our proton, we can spin that electron as fast as we want. Right? We have fixed angular momentum that we can choose, but we have an infinite choice, right? J can be any number. So it can spin faster and faster and faster around the proton. Nothing wrong with that, right? S, P, D, F, G, H, I, J, K, right? You can just keep going up the orbitals. Make it go faster and faster and faster. But no matter what you do to the electrons of these atoms, if you look at this intrinsic angular momentum that they have, the spin, no matter how, you can't change it. There's no excited state for this angular momentum. There's just 2 states, that's it. Nitrogen just has 3. And carbon-12 just has 1. Right? There are no excited states of this. They're just fixed. There's exactly 2 for the electron. All right, and so this was strange because we saw, physicists saw with the hydrogen atom, of course, that the electron's angular momentum around the proton can be any value it wants to be as long as it's an integer value. But here we have this new intrinsic thing that doesn't have, it just has fixed numbers. There's only 2 states. There aren't an infinite number of these spin states. There's just 2 for the electron. But the fact of the matter is that it behaves just like a rotation or an angular momentum. So it must satisfy the same algebra and the same rules as angular momentum. Right? So all of the same rules for angular momentum must apply here, except now we have a finite number of states. Right? There's only 2 for the electron instead of an infinity like the electron around a proton. So it's this unique angular momentum that's intrinsic to the particle that's fixed, completely and utterly fixed. Right? And I just want to talk a little bit about the physics of this and about spin. And what do we find? So what do physicists find? Is that once you start to do the math, you can figure out how many units, right? So if we think about how much angular momentum the electron has, your angular momentum has the units of h bar. So how many units of h bar does the electron have in angular momentum? What's the value of L squared for this spin, in other words? And so what do physicists find, or what do chemists find? They find that every particle has a spin. Every atom has a spin. Anything that interacts with the electromagnetic interaction has a spin. And so, for instance, the electron is spin 1/2. Now, why does it have a fractional number and not an integer number? All right, we'll come back to that. That's a product of the algebra, and I'll show you why in just a minute. Right, so that means it has two spin states, plus 1/2 and minus 1/2. Right, those are our two angular momenta. So the idea is that the angular momentum of the electron, so L for so the spin L, if you will. I haven't given it a name yet, but the L for spin for the electron is equal to plus or minus h bar times 1/2. All right, so when we measure the spin, it's some unit, it's half an h bar. Right? And every electron has an angular momentum. It either has 1/2 quantum or 1/2 unit of h bar of angular momentum, or it has negative 1/2. How do we interpret this? Well, this is not a very good way to interpret this, unfortunately, but it's a good way to think about it, I think. It doesn't get you the right mathematical answer. But the idea is that if we take our electron and we draw an axis system through it, a z-axis, right? So if our electron has this axis system through it, the z, all right, here's our little electron here. This is consistent with with a angular momentum. One of them is consistent with a clockwise rotation around the electron. This is the minus 1/2. And if we draw the same thing, draw this axis through our electron, the z-axis through our electron, the other spin state is the electron orbiting the opposite direction, plus 1/2. Okay, so we say that the electron has what we call a helicity, right? It either rotates in a right-handed fashion or a left-handed fashion. That's a good way to think about spin. Now, it fails pretty quickly because there's some things that I haven't discussed yet, but it doesn't actually work out this way. But it's a good way to kind of think about why an electron has spin, is that it kind of has a way, it can either, if you think about the electric field, if you have an electric field in this direction and the electron's propagating across that field, it can either spin in this direction or it can spin in this direction. All right, and each of those corresponds to one of the two spin states of the electron. So the electron, in some ways, is spiraling as it moves through space. And the spin state tells you whether it's spiraling clockwise or counterclockwise. All right, that's a kind of inappropriate, it's not a perfect explanation. All right, I'm not going to worry about the actual explanation. It's not that important here, but I think it gives you a good conceptual picture of what's going on. Is that what we call is that it has this what we call a circular polarization. The system is polarized in such a way that as it propagates along an axis, it spins in a circular fashion around that axis. Okay, so that's what these mean, and they're fixed to 1/2. All right, 1/2 h. If you measure the angular momentum of this electron, it comes out to exactly 1/2 h bar. Where the 1/2 comes from. And that number is, there's no way for me to tell you why it's 1/2. Well, there is. But that's about and understand where this 1/2 comes from. It takes another 4 years of physics or so, right? But we have to understand relativity and then quantum field theory, and you just have to go deep, deep, deep down into the well to understand where this 1/2 comes from. But just trust me, this comes from theory. They're intrinsically a 1/2 angular minimum of the electron. Okay. Just one of those numbers you have to remember. So how does that compare to? Right, so let's think about our other examples here. Nitrogen, the nitrogen-14 atom, it has 3, and our carbon-12 has 0, or has 1 state, right? Why is that? Well, the nitrogen atom is spin 1. It has a spin of 1. And that means it has 3 spin states. It has +1, 0, and -1. Okay? And that should explain to you immediately why it splits into 3, where 1 in the 0 state, as I call it, goes right in the middle. It has a helicity, an angular momentum, either in this way of unit 1, or in the opposite polarization, or the opposite rotation -1, or it just linear. It just moves straight. Right? So the nitrogen atom, the spin 1 nitrogen atom, has 3 possibilities. 2 helicities, and what we call a linear polarization, where it doesn't spin at all as it moves. There is another very, very important particle in the world, and perhaps the most important particle, that is also spin 1. And the other most important, and perhaps the most important spin 1 particle, is the photon. A photon, a light particle, is also spin 1. It has 3 spin states, +1, 0, and -1. Photons, light particles, can have helicity to them. And we give these a very, in classical mechanics, or in optics and light, and when you're talking about light and stuff, these have very specific names. These 3 spin states for light. +1 is what's called right circularly polarized light. -1 is left circularly polarized light. And 0 is what's called linearly polarized light. Right? I don't know if you guys have ever heard of polarization before, but I'm hoping you have. Right? But the idea is that photons also do this, right? They have a spin. Some of the photons have a circular polarization, which means that if you think about the wave function of the photon, as it propagates along the board, if you will, it spins. It has some angular momentum along that axis. Or it has 0, or it just moves straight. Right? It's very easy to prove that light can be circularly polarized, because if you polarize your light right-handed and then put a filter that filters out the opposite polarization only, you don't get any photons through it. Right? This is how polarized sunglasses work. Right? So the idea is that if you have a circular polarization of your light, you have polarized sunglasses, it reverses the polarization, only allows photons into the opposite polarization, and if you don't have any of those, you don't see anything. Right? So you can cancel out that rotation with a filter of the opposite rotation. Okay? That's the power of circular polarization. And then there are photons that just move straight like a bullet. They don't have any spin at all, linearly polarized light, which is pretty much all light. Right? The light out of these fluorescent lights, they're mostly linearly polarized. Right? They're just bullets, if you will, or just waves that don't rotate. Okay, so nitrogens have the same thing as well, and again, they have the idea is that you have a 0 spin system doesn't interact with any field because it doesn't have any angular minimum to interact with the field, or it has +or -1 where it'll go equal and opposite directions. In the photon. Okay, and why does carbon-12 only have 1 state? Well, that one's really easy. Carbon-12 is spin 0. Spin 0. So the only possible state it has is 0. It has no angular momentum at all, no spin. So carbon-12 isn't magnetic. Carbon-12 just passes through a magnetism that nothing, it doesn't care about anything, right? This is why NMR spectroscopy is so powerful for organic chemistry is because the most abundant atom, the second most abundant atom in organic molecules is invisible to magnetic fields. Right? Carbon 12s don't have absorptions and emissions, emissions in the NMR, because they don't interact with the magnetic field. Only the hydrogens do. And what's the spin of a hydrogen? Well, the spin of a hydrogen is the spin of the electron, which is 1/2. Right? So that's why hydrogens interact with the magnetic field NMR, because they're spin 1/2. They get deflected by the magnetic field. Carbon 12s don't. They don't give two shits about it, because their spin is 0. Right? This is a completely general property. Seriously, it's the most general property perhaps in the universe, is spin. There's no indication there's any deviations or perturbations. In fact, the assumption that the electron is a point that has -1 charge and spin 1/2, that is good to about 1 part in 10 to the 35. And people keep looking for the electron to have some sort of asymmetry, if you will. That it isn't just a point with a fixed spin. People have gone deeper and deeper and deeper and deeper and deeper, 10, 12, 15 significant digits. And we don't see it. It's one of the most precise measurements ever done. This is one of the best hard rules in all of science, is spin. You can't get rid of it. It is what it is. And it's a very subtle point, and it's one that I don't think that we can really appreciate just yet. But so much of chemistry is defined by spin. It's hard to see that. But the fact that electrons have a unique spin, and the fact that electrons can either be spin up or spin down, can affect things dramatically in chemistry. Very, very dramatically. In fact, if you're looking at an iodine, for instance, one of the reasons why that peak that you're observing in the iodine spectrum is explicitly dependent, why it's so intense, is explicitly dependent on the fact that the electron has spin. Very, very subtle point, but it is true. So I want to just talk a little bit more generally about spin in the last 15 minutes or so. Again, there's really not much math that we have to learn about spin. The math is exactly the same as angular momentum as before. The rules are exactly the same. So let me just talk very briefly about the quantum mechanics of spin. So we're going to define two operators. Right? Spin is like angular momentum. So we need to come up with a magnitude and a direction. So let's do exactly the same thing. We're going to define a spin operator, magnetics operator, such that when we apply it to our wave functions for, say, our electron or whatever, that we get h bar squared times s plus 1, okay, where s is the spin of the particle. Okay, so for hydrogen, or for the electron, so example, s squared for the electron is h bar squared times 1/2 times 1/2 plus 1 psi, which is, what is that? That's 3/2 times 1/2 is 3/4 3 h bar squared over 4. Okay? So an electron has a fixed angular momentum. It's always 3, the magnitude of its angular momentum is always 3 h bar squared over 4. Every electron, for all intents and purposes. And then we also need to know the direction. So we'll define an operator S sub z that when we apply to our wave function for our system, we get h bar times a projection quantum number m sub s times psi. Okay? And just like in quantum mechanics, or in angular momentum, let me just write this out explicitly, that m sub s can be any value from -s to minus s plus 1 to s minus 1 to s. Okay, so let's try, what are the allowed values for m sub s for the electron? So if we apply sz to our electron, we have two options, right? We get an h bar, and we get anything between s and minus s, different by 1. So the first result we can get is m sub s equals plus 1/2. And then let's subtract 1 from that. What's 1/2 minus 1? Minus 1/2, well, that's minus s. So there's only two options. There we go. We've already reproduced all the physics of the electron spin. Electron has spin 1/2. S is 1/2, it's fixed. And therefore, there are only two possible spin states, plus 1/2 and minus 1/2. Remember what I said about the difference between the projections along the z-axis of angular momentum. One is clockwise rotation, the other one's counterclockwise rotation with respect to the z-axis. Exactly the same thing I said here, right? One's right-handed helicity, the other one's left-handed helicity. One rotates clockwise, one rotates counterclockwise. Right? And that comes from the fact that there's two projections. Two states. And two states only. Okay, so let's just try one more example. Let's just do the nitrogen atom and just convince ourselves that all this math works out. So one more example. Nitrogen, which has s equals 1. Okay, so that means s squared is equal to h bar squared times 1 times 2. So it's 2 h bar squared. And s sub z can be anywhere between s, which is 1. What's 1 minus 1? 0. What's 0 minus 1? Minus 1, which is minus s. There are three states. Three spin states for 14 nitrogen. So easy, right? The algebra is so simple for this. Right? And so spin is exactly the same as angular momentum, except that s is fixed, right? S is the equivalent of J here. J could be any value for the electron around a proton. Right? You can just spin the electron faster and faster and faster. Spin is intrinsic and fixed. So S is the same for every of those types of particles. Right? Every electron has S equals 1/2. And that fixes the fact that there are exactly two spin states of the electron. Spin up, as we call it in orgo, and spin down. What I want to say, right? And so I don't really want to go too much deeper into spin right now until we start talking about the hydrogen atom explicitly, but it's good to know that the electron and the proton, they both have spin 1/2. All right, so the proton has some angular momentum, and the electron also has some intrinsic angular momentum from spin. And so what happens, for instance, now I'm not going to answer this question yet, but I want you to keep it in your head. Imagine, let me put it this way. So let's just do kind of a thought experiment here for a second. All right, so let's look at the hydrogen atom. Again, we don't really know a lot about it yet, but we do know how it works angularly. We have a proton, and we have an electron here, and I'm gonna kick that electron and spin around it. All right, so we're gonna set the electron. Let's just say, for instance, let's let the J for the electron to be 1, which means that L squared for the electron is 2h bar squared. Okay, so this is the angular momentum of the electron around the proton. Okay, that's what I mean by J here. That's what we talked about last class. Okay, so now Well, I haven't considered the spin at all. But as this electron is spinning around the proton, the electron itself is spinning as well. Right? It has spin. Right? So we have an additional angular momentum to our system. Which is 1/2. Right? So what's the net angular momentum of the system? Well, we have two angular momentums we have to add together. Right? The electron has some torque from the proton causing it to spin, but the electron itself also has some torque from the spin itself of the electron that's also contributing. So the total angular momentum of this system is going to be J plus S. Right? So, or at least that's a good way to construct it, right? And so that would mean that if that's the case, then the net angular momentum of the system is 1 plus 1/2. It's 3/2. Okay, but there's also the option that the spin is minus 1/2 too, right? Right? This is plus or minus 1/2. So we can also have the result of J plus the opposite minus S, which is 1/2. Okay, so when you add spin to an electron that has its own, what we call orbital angular momentum, we're going to have to redefine these symbols eventually to compensate for all these different angular momentum. You think about J as being the angular momentum of the orbit, orbital angular momentum. Then a p state, if you will, right? Well, that's what J equals 1 is a p state. There's actually two p states. There's a p state where the electron the angular momentum of the electron is adding constructively to the orbital angular momentum, which gives you a net angular momentum 3/2, or it adds destructively to the angular momentum, slowing it down, giving you 1/2. So this means that for every p state for an electron, it's doubled. There are 2 states for every J state, right? Because of the spin. And those are the only 2 options. You guys know this is the case. How many electrons can you put in a p orbital at one time?
6.
Oh, one of the 3. Yeah, so 6 total. Right? There's 3 p orbitals, right? So you can put 2 in there, right? You can either fit an electron with plus angular momentum, spin angular momentum, or one of negative. So there's exactly 2 for the electron, exactly 2 p orbitals. One for the spin up and one for the spin down. That's why we have the Aufbau principle, where we fill orbitals with pairs, right? We add them one at a time, and we can only put 2 at a time. And it's partially because of the fact that the angular momentum, that there are effectively 2 angular momentum states. There's one where the spin adds with the orbit, and one where it works against it. Those are our 2 states. So again, I've now, without even thinking about the hydrogen atom and its radius and stuff like that, I've only considered angular momentum. I've already reconstructed all of the orbital structure except for n, right? 1s, 2s, 3s, 4s. I haven't gotten that number yet. But I've gotten the fact that the orbitals have this spherical behavior, right? The SPDF. And I've gotten the fact that you can fit 2 electrons into each orbital. And only 2, because there's only 2 possibilities. Right, so I've already recreated 3/4 of the hydrogen atom structure. I just have to get the radial part next. This ends up having very, very deep consequences that's kind of hard to see until we start thinking about the hydrogen atom completely. And what we're also going to realize is that we can also, for instance, add the spin of the proton. The proton could be orbiting itself in the same direction as the orbit of the electron, or it could be working against it. And that will also cause the orbitals to split into two. So there's actually 4 of them. Actually, there's 3 of them. 2 of them are at the same energy. But you can think it takes, what we've done is we've taken one p orbital and we split it into a doublet, and then when we add the proton, they split into a quartet. It's a doublet of doublets. So each of these angular momentum can be added and subtracted to each other, and that causes complications in the way that the electrons can arrange themselves in an atom. Right? And it just comes from these angular momentum rules. Very, very simple rules. It's very simple algebra. Just integers and fractional numbers. Right, I have one more thing I want to mention before the end of the class. Just very, very simple qualitative idea. We're not going to worry too much about the consequences of this, but it's a good thing to know. So you may have noticed that there's actually kind of 2 classes of particles of spin. There's ones with what we call integer spin, spin 1, spin 2, spin 3, and then there are these fractional ones, 1/2, 3/2, 5/2, 7/2, 1.5, 2. However you want to look at it. So there's some that have integer spin and some that have fractional spin, and you might think, okay, well, does that really matter? And it turns out it has very, very deep consequences, that these 2 different types of particles act very differently. And we're not going to talk too much about why that is, but I think it's important to name them and also talk about the consequences. All right, so there are 2 classes of, I like to say, spinning particles. I think it's better to call it particles with spin, but I like spinning particles. All right, there are the ones that have fractional spin. So that's like the electron, the proton, the quark. Most things are fractional. Actually all but 1 or 2 fundamental particles are not fractional. So the Higgs boson is spin 0, and the photon is spin 1, and I think those are the only 2 naturally occurring subatomic particles that have integer spin. The rest of them have fractional spin. So the vast majority of matter in the universe has fractional spin. So this is, say, for instance, S equals 1/2, 3/2, 5/2, and so on and so forth. These are called fermions, after Enrico Fermi. Fermions, and ones that have integer spin which is S equals 0, 1, 2, and so on, are called bosons after, I forget his first name. He worked with Einstein. They're not called Einsteins, unfortunately. They're called bosons. Nagendra Bose. He was an Indian physicist who discovered the statistics of bosons and figured out the physics of them. They're named after him. And Fermi came up with the physics for the fermions. And the difference between bosons and fermions, of course, is their spin, but they have a very, very important consequence that you can't get from the fact that they have integer. You're like, why is this a consequence of this? But it is. Very, very important consequence. Big consequence. Only one fermion can coexist in the same state in space at the same time. What does this mean? This means that if I take 2 electrons that have spin on them, everything's the same about them, right? They got the same angular momentum, everything. And you bring them close together, it's impossible to put them on top of each other. Remember, electrons are points, so they don't really have any space. So you can think about putting 2 electrons in the same spot, right? Because they're fermions, if they're both the same if they're both the same spin, they can't exist in the same state at the same time. Okay, so for a collection of electrons, every electron has to be at a different position or in a different state of some sort in order to coexist. Okay, so you can't have two electrons at the same energy level with the same spin, right? That's why, for instance, you can only have 2 electrons per orbital, right? Because an orbital specifies the position and the energy of the electron, and we can have one that's spin up and one that's spin down, and that's it. So a spin up and a spin down electron, 2 fermions of opposite spin can coexist in the same space, but not 2 fermions of the same spin. All right, that's why you can only have 2 electrons per orbital. That's another reason why, at least. Maybe the bigger reason why. You only have 2. Now bosons don't have that limit. However, bosons are free to coexist in arbitrary numbers sharing the same state. Okay? So if electrons were bosons, then there would be no atoms. There would be no valence shell. Everything would be in the 1s state because you can have infinite number of electrons in the 1s state. They can all have the same spin, the same angular minimum, all exist in the same state. Every atom would be precisely the same, except they would just have different number of electrons, but they would all have the same energy. There would be no temperature. The universe would have no energy. At least I don't think it would. There certainly wouldn't be any atomic matter or chemistry because every atom is in the ground state. And the ground state is every electron in the atom in the 1s orbital. It's a pretty boring atom. Right? So the fact that electrons are fermions is the exact reason why chemistry exists in the first place. We wouldn't have the periodic table if it wasn't for the fact that we can only fit 2 electrons per orbital. Right? There's really, really interesting consequences of this. For instance, if you take certain types of bosonic atoms, helium-4, classical helium, for instance. Helium is spin 1, which is spin 0. I forget. Spin 0. Helium is spin 0. If you cool helium down to low enough temperature, it becomes what's called a superfluid. What is a superfluid? Well, it's a liquid where all of the atoms in the liquid have the same they have the same state. They're all in the same state, which means they're all moving in the same direction. They're all perfectly correlated. Everything is exactly in the same state. There's no mixture. The entropy of a superfluid is 0 because there's no mixture of states. All of the helium atoms are in the exact same state in their ground state. Therefore, the entropy is 0. It's a 0 entropic material, or at least asymptotically 0. Of course, the entropy can't be 0, but it's basically minimum. Right? You can't do that with fermions. Well, you can, but you have to cheat. Right? In order to get the same behavior of fermions, you have to go even lower temperature, and that's a really crazy effect that I don't want to talk about. But anyway, bosons are allowed to do this. And in fact, one of the most violent, I'm just going to say this one more, just 10 seconds. One of the most violent consequences of this result are supernovas. The source of a supernova of a star, so only stars of certain large mass, I think it's 1.4 solar masses, so the atoms are 2 solar masses or so stars larger than the sun, only large stars can go supernova, and what happens is, what a supernova is that as the star dies, it sheds off all of its atoms, everything, until all that's left in the core are just electrons. And as the mass, as the star starts to expand, because that's what happens as it dies, it gets bigger and bigger and bigger and heavier and heavier and heavier. And it presses those electrons together more and more and more and more. But electrons don't want to be pressed together. They're very, very, right? If you think about a metal, it's like a metal of pure electrons in the core of the star, this dying star. It's very incompressible. Electrons don't want to be in the same state. They repel each other because they're fermions. They don't want to exist in the same state. And eventually that force becomes so great that the only thing the electrons can do is shatter. Right? That lattice of electrons shatters. They can't be squished into a single point. They have to be destroyed. That's the only thing they can do. Because energy goes to infinity as the electrons get closer and closer together. The only thing that's left to do once the pressure becomes so great inside that star, the dying star, is for the entire lattice of electrons, if you will, to completely shatter, and then you suddenly get the most violent explosion known to mankind, right? So violent that you can see it in other galaxies. Sometimes you can look up at another galaxy, well, you can't with your eyes, but with a telescope, you can see a bright dot appear out of nowhere in that galaxy 100 million light years away. That's a supernova. It's one of the most violent explosions in the world, in the universe. And that's entirely because electrons are fermionic, because you can't compress them together. If you compress them too hard, they shatter and they explode. And that's entirely a consequence of fermionic behavior. Okay, I've gone too long. You guys have a lovely weekend. We'll come back to this. We'll finish up the radio problem on Monday. We'll have a beautiful model for the hydrogen atom on Monday, and we'll be able to look at these things more carefully. All right, have a good one, guys. Good luck on the exam.
Yes, see you tomorrow, bro.
Yes, sir.